Welcome to the Supergen Bioenergy Hub's webinar on temporal and accounting aspects of greenhouse gas emissions. My name is Marcel McManus and I'm from the University of Bath, and I'm also part of the Supergen Bioenergy Hub. Today, we are really pleased to be able to have this webinar on temporal and accounting aspects of greenhouse gas emissions. And first of all, I would like to just go through a few things about the Hub and what the Hub does and how we work together. So if we could have the next slide, please. Thank you. So the Hub is directed by Professor Patricia Thornley at Aston, and we have 4 topic groups, as you can see here. The first one, resources, is led by Ian Donaldson at the University of Aberystwyth with Rebecca Rowe from CEH. The second is the pre-treatment and conversion, led by Jason Hallett at Imperial and Chris Hardacre at Manchester, with Tony Bridgewater and Katie Chong at Aston. The third topic group, vectors, is led by me, Marcel McManus at the University of Bath, along with Andrew Welfle at Manchester. And the final topic group, the systems topic group, is led by Miriam Roeder along with at Aston, along with Rob Holland at Southampton and Andrew Welfle from Manchester. And together we work together to look at how we really understand the different aspects of bioenergy, really taking a holistic view through the use of case studies to work with industry, policymakers, and engaging with the wider society to understand the benefits and impacts of bioenergy. Today, we're going to be focusing particularly on the temporal parts of the bioenergy systems, and we've got some really interesting talks from Sam Cooper at the University of Bath, Andrew from Manchester, and we've also got Mike from Drax and Nicola from the Roundtable of Sustainable Biomaterials, and I'll introduce these speakers as we go through. A few things just to go on with about the webinar. Please ask your questions via the Q&A that you can see. It's on the right hand side of my computer. I think it should be in the same side for you, but you can find the panel questions. If you have a question about a particular presentation, and this is a clarification question, then we'll have a quick moment at the end of individual presentations for these questions. However, if it's a broader question, then we will leave it to the end of the session where we have the panel session. So, as I said, we've got 4 presentations followed by the panel discussion with all of the presenters moderated by myself and Miriam. You can like any question that's been published. We have had some questions in advance as well, and we will try to go through all of these and answer these. And we will be recording the webinar, and we will share that recording with attendees afterwards, and we will make it available online. And if there are any particular questions that you don't get answered today, feel free to let us know, and we will do our best to answer any of these at a later date. Okay, so without further ado, I would like to introduce our first speaker. So first up, we have Dr. Sam Cooper from the University of Bath, and he is going to be talking about the effect of timing on impacts of greenhouse gas emissions. So over to you, Sam.
Brilliant, thank you. Cool, can I have the next slide, Katrina? Brilliant. So when I think about climate change impacts and greenhouse gas emissions, I'm often tempted to imagine these two things happening at the same point in time. So I imagine, say we have an emission of CO2 today, and that it's getting warmer and everything's happening today. And sometimes that's convenient to kind of put those two things together in our minds. But of course, that's not really how things work in real life. What really happens is we have an emission, and then after that emission of greenhouse gases, we have climate change impacts that vary with time afterwards. And so if we emit some CO2 today, then there will be a climate change impact which happens over this next year, and then there'll be a different impact occurring the year after, and so on and so on. In fact, it's more complicated than that as well, because the way in which these impacts vary with time is different for different gases. So there'll be different dynamics associated with, say, CO2 emissions compared to methane, compared to nitrous oxide, and so on and so on. Each of these gases will have its own dynamics relating to the climate change impacts that it causes. And as well, when we talk about climate change impacts varying with time, the way in which it varies depends by what we even mean by climate change impacts. So we might be interested in radiative forcing and a kind of like a gross heat input into the atmosphere, and that will have certain dynamics. We might be interested in, say, temperature change, and that will have its own dynamics as well. And those dynamics potentially can be quite different. So what we see is that even if the emissions happen at a single point in time, the dynamics associated with the impacts that those emissions cause can be quite varied. Next slide, please. But added to that, we have an effect where, of course, emissions aren't necessarily happening at a single point in time. For a lot of systems, especially when we're looking at bioenergy, we have emissions which may occur over an extended period, and they might vary. We might have net emissions one year and then certain absorptions at certain points, and so those can be quite complicated dynamics as well. And so we have this situation where potentially we're combining emissions that vary with time with impacts due to those emissions that also vary with time after those emissions. And so we kind of get this question, and I was trying to think of like a clever punchline, and I couldn't think of one. So if anyone has a funny idea, then maybe you could put it in the comments and I'll read it out later. But essentially the point, which is hopefully becoming clear, is that for some systems the dynamics are very complicated, and the way in which the impacts vary with time is quite complicated, it's quite involved. There are some systems where it's fairly straightforward and we can use a single metric like, say, CO2 equivalency based on greenhouse global warming potential. And that's got its place, and it's a very good way of doing things. But there are lots of systems where a single metric, or maybe a couple of metrics, they just can't capture the full dynamics of what's going on. Okay, so I mean that's really the main point, and that's a bit abstract. So we're going to try and make it a little bit more concrete with a couple of examples. Can we have the next slide? Awesome, thanks. So so here, this is an example looking at so using bioenergy for heating. It's actually for a district heating network, and it's just a couple of bits of work that a colleague did a couple of years ago. And here there's a couple of options being considered. There's anaerobic digestion, or there's forest residue wood chips. And for these examples, all of the actual emissions occur in year 0. So it's kind of like a pulse. So this is just dynamics associated with the gases themselves. There's nothing to do with emissions happening at different points over time. So we have the emissions occurring in year 0, and then at year 100 we are saying, well, what is the impact after that period? And we could think of it in absolute terms, or here also what's often done and is convenient is to think of it in terms of CO2 equivalency. So what is the equivalent CO2 emissions from year 0 which would cause that impact, the same impact, in year 100? And in this example, the top line is thinking sort of integrated radiative forcing, so kind of like a gross heat input into the atmosphere, if you like. And those results are pretty similar. If we think about temperature effect, well, they're a little bit more different, but they look kind of robust. And so this got us thinking, well, it'd be interesting to think, well, what is the impact, though, not just at that 100-year point, but in all of the intervening years? So next slide, please. And this is kind of what we see. And this is really what got me thinking, actually, this is something we need to look at a bit more. And this is kind of unintuitive. So we see the dotted, the kind of dashed green line, that's the forest residue example. Well, that's fairly straightforward. We're seeing a fairly linear, it's roughly a linear increase in the integrated radiative forcing year on year. And after the first kind of couple of decades, the temperature effect is also fairly constant for that forest residue example. But if we look at the anaerobic digestion, actually the results in the intervening period, especially the sort of 20, 40, 60-year period, they're all over the place. And there's no way I would have guessed that from those initial point results, which are what would be typically reported. So really the point here, again, just to try and emphasize that for some systems, those single metrics, they can work. For other systems, they just don't capture everything that's going on. So next slide, please. So another example here, we're thinking, well, what do we mean by CO2 equivalence? And CO2 equivalence is a really convenient way to think about greenhouse gases and to sort of capture quite a bit of information. And obviously it's used very broadly, and so it's widely used. The concern here is that potentially sometimes we are using it to mean one thing or to answer one question, when really potentially, maybe not explicitly, but implicitly, we're kind of thinking about a slightly different question. So this is an example just to kind of try and explore that a little bit. It's actually based on a short rotation coppicing case study that Miriam did a couple of years ago. But essentially, you have for individual forest stands, you'd have lots of year-on-year variation, but across the whole forest system, it all kind of levels out. And so what we see is a fairly modest annual emissions due to the system, just within the kind of assumptions of the system. And so that results in this black line, which is the cumulative emissions. And obviously, year-on-year, it's just going up by that modest increment. And this would be kind of by definition what the CO2 equivalence is for it, by the sort of the normal understanding of CO2 equivalence. And so the first point even to notice here is that the actual change in atmospheric greenhouse gases here it's almost entirely CO2. It's far less. A lot of that CO2 is reabsorbed by other systems during that 100-year period. So next slide. Thanks. So, but then we could also think about CO2 equivalents in other ways. So, for example, here we might like to think for a given year within that period, or even going beyond it, how much CO2 would need to be emitted in year 0 to have an equivalent effect, either temperature or heating integrated radiative forcing by that year. So by year 60 or whatever, how much CO2 would need to have been released in year 0 to have that effect, the same effect as our system by that year. Or, so next slide. We might stick with our 100-year time horizon, and we could think, well, how much CO2 would need to have been released in year 0 to have the same effect by year 100, again in terms of temperature or heat, gross heat, as our system by a given year. And there's lots of ways to think about this. And my point isn't so much to really go into detail of these different calculations, but just to demonstrate that there are differences, and these would come up with, as you can see, fairly different results. And while one of them is the standard way, that the black line would be the standard accepted way of doing this, it may be that other questions relate better to other metrics. Okay, next slide, please. So where does this leave us? Well, I think there's a couple of things which we've learned. The first is that our intuition for these systems is not always reliable. We can have a single point result, and we don't always know what's happening in the meantime. We don't always know the full picture, really. And I guess similar to that is that single metrics, obviously they have their use, and if you've got nothing else, that's clearly a very useful thing. But they can't capture everything. There's just no way that some of those dynamics can be captured by just one or just two, as would be a little bit better. But those dynamics just can't be captured by that. And so I think this leads us to sort of thinking, well, how do we balance this need on one hand for simplicity and being able to communicate to a wide audience and to compare results with, on the other hand, a need for transparency and actually making sure that effects which are there are not just lost in the way that we're communicating it. And I think this is an open question. I think this is something where we were looking at the people who hopefully you're here attending this webinar, and it's humbling the expertise that you represent. So I'd be really keen to hear afterwards by email or whatever, like if you have thoughts on this, because I think this is something which going forward we need to improve on and think more about for certain systems. Okay, a couple of kind of examples for how we might think about this. So we could I guess it's best practice anyway, but to try and increase the amount that we are providing full emissions inventory with our results. So not just a sort of a CO2 equivalence based on whatever we wanted to use for that, but actually what are the emissions which are causing those impacts? That would allow people to look back at the results and interpret them for other sets of assumptions, or other, perhaps if the question actually is a little bit different. The second thing is really just to compare whether or not there are complex dynamics. Next slide, please. Yeah, cool. So, I mean, one of the things which I really feel in doing this is that on the one hand, we have like the climate science kind of discipline, and where all the things which I've just described, they're not novel, they're all well described throughout the literature, and especially, I mean, well summarized in IPCC reports and so on. So there's nothing new there in a sense, but I feel that then on the other hand, we have kind of maybe us in the LCA world where we're busy and got reports and everything to do, and so we might become aware that there's this kind of temporal effects going on, but actually the opportunity to explore them a little bit more, it just stays, if you like me, it stays on our to-do list. And so what we wanted to do is provide like a spreadsheet. So that second link there is a spreadsheet where you can just put in sort of numbers relating to different gases occurring at different times, and then just kind of explore, hopefully in a pretty transparent way, what the actual impacts relating to those emissions are over time, and just kind of get used to it and see whether in terms of reporting stuff, whether a single metric is sufficient or whether it kind of masks things. So hopefully that'd be useful, but I'd certainly welcome comments and suggestions on how to make that better. So yeah, thank you. So as I say, so the main point here really is that these impacts are varying with time. They can be complicated, and moving forward, it's just important that we're aware of that, and we're making sure that the questions we're asking fit, and the answers and the results actually are answering what those questions are. Thank you.
Thank you very much, Sam. That was excellent. Right, we have, can I just ask everyone to remember that if they have a particular question for clarification about a presentation, if you could start off by marking it presentation, that would be really helpful for us. Anything else, mark it with panel, otherwise we will decide ourselves which way it goes. So Sam, before you head off, I have one clarification question for you, which is, what is the explanation for the different dynamic responses on the chart showing the AD and forest residue effects?
Oh, thank you. Yeah, that's a good question. So yeah, so there actually what's happening is the AD plant. Essentially, within the assumptions of that study, we're seeing avoided methane emissions at year 0, and also slightly greater CO2 emissions. That's the one. And so basically, it's down to the dynamics of those two gases, meaning that it just happens. It's kind of like fortunate for us in a way, but that at year 100, those two effects kind of cross over, and that's what's causing the early effect. I mean, in a sense, that's quite a specific example, but the point is really more to illustrate that there are effects that can happen at different points in time that we just wouldn't be aware of if we're just given the overall results. Thanks.
Excellent, thank you very much. So we have no more clarification questions for Sam, but Sam will be on the panel at the end of the webinar, so we can still ask lots of questions about this very exciting research area at the end. So next up, we have another presentation from the Supergen Bioenergy Hub, from Andrew Welfle, who is at the University of Manchester. He is also a member of the Supergen Bioenergy Hub, and he is researching in the systems topic. And Andrew is going to be talking today about the whole life cycle bioenergy emissions within the UNFCCC emission accounting framework. So over to you, Andrew.
Thank you for the introduction, Marcel. So I'll go straight into it. The next slide, please, Katrina. Okay, so what is bioenergy and how is it a low carbon renewable energy option? So basically, for bioenergy to be a viable low carbon option for energy, it needs to replace fossil fuels, and it's fundamental that the GHGs it emits provide genuine reductions in emissions. And the concept of this emission reductions comes around the fluxes between the atmosphere and terrestrial systems of movements of CO2 and greenhouse gases. For bioenergy, there's two main categories of gases which are really important and are going to be important in this presentation. So you've got biogenic carbon emissions, and these are related to the natural carbon cycle. And then with each bioenergy system, there will also be processing emissions. These are the emissions that result from energy being put in within the process, resulting from activities such as harvesting or processing of the materials. So yes, to summarise, bioenergy will be low carbon provided that there is a close balance between the emissions released to the atmosphere with those stored within a plant as the plants grow. So basically, it's really important to account these whole life cycle emissions if we are going to ensure that bioenergy provides a viable option for meeting our GHG emission targets and to basically getting rid of fossil fuels. Next slide, please, Katrina. So basically, this here is our take on the carbon cycle. The carbon cycle is something which I'm sure many of you are very familiar with. So basically, the CO2 in the atmosphere is put in the atmosphere by man-made activities such as numerous natural activities. So the concept of bioenergy is that CO2 in the atmosphere may be captured within organic materials through the process of photosynthesis. Plants, that organic material may be stored within all sorts of organic materials, forestry, woods, animals, plants, etc., etc. And with those organic materials, at the end of their life, they would naturally decay, and that CO2 would be eventually released back to the atmosphere. Bioenergy, or using those materials for products, kind of short circuits that larger cycle. So that carbon could be stored within products such as chairs, furniture, whatever it may be, as a way of storing it. But then again, at the end of the life cycle of those materials, the carbon will more than likely end up back in the atmosphere. Or bioenergy provides an even shorter cut, where you can take that organic material, create some energy from it, and release it back to the atmosphere. So the secret of bioenergy being a low carbon energy option is ensuring that the balances of those flows are favourable and they provide less emitting of CO2 to the atmosphere compared to fossil fuels. Next slide, please, Katrina. Thank you. So basically, bioenergy is quite a special case because it's becoming more and more an international renewable energy option. So I'm focusing on the UK because that's where I'm sat now. That's where much of my research focuses on. The UK sees bioenergy very favourably, and they have targets to increasing it. So currently, as of 2018 data, 31.6% of the UK's renewable power comes from bioenergy, 41% of our renewable heat from bioenergy, and we have a small but growing, fastly growing contribution of biofuels to our transport energy mix. So the bioenergy is on the map in the UK and it's growing fast. But the UK biomass feedstock demand as a result is currently growing very fast, and that's largely driven by international supply chains where we import biomass into the UK from many regions. The UK is actually currently consumes about 20% of global forest-based pellets, making it the largest consumer worldwide. And of the pellets we consume in the UK, many of these come from abroad, over 90%. So it's really important that we kind of map out from the UK's perspective, or for any country that's importing these biomass for energy, where these emissions are taking place and whether they are indeed resulting in an overall net benefit to the atmosphere to meet our climate change targets. Next slide, please. So this diagram here is basically to highlight the complexity of bioenergy supply chains or bioenergy processes. So normally somewhere in the world, whether it's in your own country or in another foreign country, there will be some kind of production of biomass material, forest, a plant, organic materials. There'll maybe be a net movement of CO2 from the atmosphere to those sinks. We're going to be expending energy, we'll be processing those, mobilizing that material. So fuel energy will probably be expended there. There may be transport steps, moving that material from one place to another, where we create energy and maybe CO2 emissions are generated. That material may be taken to a central site to produce a biofuel, whether that's a pellet, a chip, a biogas, a biofuel. So energy is going to be put in there, potential for flux of emissions to the atmosphere. If we're importing the resource, there may be some emissions as that biofuel is transported across international borders, maybe across the sea. Finally, when it comes to its end destination, that fuel will be converted into bioenergy, and those biogenic emissions will be released back to the atmosphere. And then finally, at the end of that process, there may be some wastes where we may need to put some active energy into process or to remove or to clean those wastes. So each step within a bioenergy pathway, there will be energy put in, there'll be emissions going both directions. And the science of much what I do and what my group do at Supergen is accounting what the balance is of those emissions over this whole process. That can be highly complex because these supply chains are getting more and more complex. Next slide, please. So basically, the UNFCCC's emission accounting framework has been developed to try and account this. It's not been developed for bioenergy, but bioenergy kind of neatly or not so much fits within it and how it accounts emissions. So basically, the IPCC oversaw the development of this university adopted methodology for accounting emissions at national scale. So nations are basically required to individually account and report their emissions within a series of GHG inventories, and these are submitted to the UNFCCC for verification. So basically GHGs are accounted within different inventories, and these are divided into sectors and subsectors. For example, the main ones are energy, activities associated with industry process and product use, activities associated with agriculture, forestry and other land use. You've got all the waste inventory and then another inventory, and within each of these there are categories and subcategories. For example, transport, a subcategory of that would be cars. And basically this framework provides a comprehensive method for basically measuring, reporting and verifying emissions within, and then there are different requirements depending on whether it's a developed or a developing country, of which the IPC documents will provide you much information of how the reporting mechanisms are different. So how does this work for bioenergy? If you go to the next slide, please, Katrina. I decided to include this table here. It's a snapshot of one of the IPCC guidance documents. So basically, there are different approaches for how emissions are accounted for harvested wood products, which something like a pellet is, if it's a bioenergy. So there are approaches of accounting, whether it is assuming a steady state of a product pool, whether there's a stock change taking place of emissions, whether there's a production approach or an atmospheric approach. These are different approaches of how you account emissions within the framework, and depending on which approach you take, the emissions will be accounted differently. And then again, on the left-hand side, there are different types of resources. So for example, if you're producing a biomass resource, which is going to be used specifically for energy, that would be accounted in a slightly different way if it was a waste or residue from an ongoing process, or something collected from a forest floor that was otherwise okay. So there are slightly different methods for accounting bioenergy within the system according to the approach you take, and also according to the feedstock or what it is, which makes it very complicated to get your head around. But I'm going to try and clarify that in the next few slides. Next slide, please, Katrina. So in essence, bioenergy versus the accounting framework, how does it all work? So basically, the three main categories where emissions are accounted are the agriculture and forestry category inventory, the energy emissions inventory, and the waste inventory. And pretty much in the agriculture and forestry inventory, much of the emissions are accounted here from wherever they take place in the world. So you have biogenic emissions, CO2 will be sequestered through the growth of the biomass, and it will be released back to the atmosphere. So within the agriculture and forestry inventory, we will be accounting the growth of the forest, as in its uptake of carbon. And if we're producing a product specifically for bioenergy, we'll also account that as a positive and a negative. So it'll be neutral for that inventory if we're producing resources for bioenergy. Also within that sector, we account things such as land use change or indirect land use change. That may take place straight away, or may take place several years after the account. So anything associated with the land, agriculture and forestry resulting from bioenergy processes will be accounted within this inventory. Annual crops are counted a bit differently because they assume that they will be replaced each year and there will be a net balance. The energy emissions inventory is a bit different because any biogenic emissions released to the atmosphere through the combustion is not accounted in the energy emission inventory. It's actually accounted in the forestry and agricultural one. But what we do account within the energy emission inventory is emission non-CO2 emissions such as CH4 and N2O. These are accounted in those, and any energy that's put in through the whole process, whether that's fuel energy for a truck, a plane, processing of a material, any of the energy or CO2 associated with that is accounted within the energy emission inventory. Emissions that take place outside or between national boundaries, such as a ship going across the ocean, they are accounted, but they're classified as international bunker fuels. And finally, the waste emission category. Any waste occurring over the process and degradation of materials are accounted within the waste emissions inventory. So, for example, if there are residues which are left in the forest floor that degrade, it will be counted there. If there's any energy recovery from processing of waste, it will be counted in the energy inventory. But if there's no energy recovery when you're processing waste, it's accounted in the waste emission inventory. So it's quite a complicated picture, which I'm going to explain in the next slide, I think. Next slide, please, Katrina. Thank you. So yes, as I said, the scale of traded biomass has increased and international supply chains have become more and more complex, which means that how we account GHG emissions associated with bioenergy is becoming under greater scrutiny, which is potentially the right thing that should be. but there is a growing common scenario where we are transporting more resources across national borders, and we're converting resources to bioenergy in a different country from which that material was grown. As a result, the life cycle steps take place across many different international borders, and the emissions they generate will be accounted within the GHG inventories of those countries differently. So it's really hard, it can be really hard to account what's the overall impact of a bioenergy pathway, because those emissions will be taking place A, in different countries, and B, within different GHG inventories within those countries. So we developed an idealized graph on the next couple of slides, which basically highlights a scenario where a country A is producing bioenergy from pellets imported from country B, and we're going to basically highlight where the emissions take place and where those emissions are counted according to the framework, IPCC framework. And just to highlight as a caveat, we are assuming that this material has been produced directly for energy use, so we're using the correct IPC methodology for counting those emissions. So we go directly into the next slide. So this graph here basically demonstrates where emissions will actually take place. If you look on the far left, these are emissions taking place within country B, where the biomass is being produced. In the middle, we've got emissions taking place between countries, as in international waters, as they're transported. And on the right, you've got emissions taking place within country A, where bioenergy is actually being generated. So where emissions are actually taking place in country B, there will be an uptake of emissions or CO2 from the atmosphere as forests grow, and it's locked up within that carbon store to produce forestry material. But then the red on the right basically is fuel energy, so there'll be some energy dispensed harvesting that material, turning it into wood pellets, and there may be some waste material as well also taking place within country B. In the middle there, you've got the red, small red, that is fuel energy expended between international borders, basically shipping something from A to B. And finally, on the right, you've got the emissions taking place in the country where bioenergy is taking place. So you've got the release of biogenic emissions there, again, which is the big orange, and then you've got some fuel energy and some waste, etc. So this is an idealized graph, and the dotted line there represents of this idealized scenario what the overall balance would be for this carbon emissions. So as long as that balance is pretty much that dotted line is below a fossil fuel equivalent, then bioenergy would be delivering a good option for replacing that. But of this scenario, how are these emissions actually going to be accounted within the different countries? So if you go to the next slide. So basically these are the same, this is the same amount of emissions, but this demonstrates how and where they are accounted in terms of GHG inventories. So again, we have on the left the country where biomass is being produced. In the energy sector, any fuel energy used will be counted in the energy sector. Within the forestry inventory, we've got uptake of emissions through production of forests and expansion of forests. And then because we're producing, for this specific case, we're producing fuel that's going to be used directly for bioenergy, we also account those emissions above the line. So it's overall neutral for forestry inventory for this particular activity. You also got some waste emissions in the country where biomass is being produced. Bunker fuel emissions are counted and labelled as such, bunker fuel emissions. Within country A, where we're actually producing energy, the noticeable difference is that, yes, we do account emissions associated, non-CO2 emissions, CH4, N2O, within the energy sector inventory as that bioenergy is converted. But noticeably, the biogenic emissions are on the far right there. They're not accounted within country A's GHG inventories, but they are listed as a memo item. So they're on the page, but they're not actually included within the actual emissions. But that's fine, because if you take that far right column away, you've still got a balance overall there of the overall cycle. If you go to the final slide, please, Katrina. So this IPCC approach for accounting GHG emissions for combustion, it's quite effective. It can be quite effective at looking at biomass or biomass-based products such as ethanol or wood pellets, and it can provide complete coverage of emissions and removals across the different sectors and across international boundaries. In GHG accounting terms, it can provide an attractive option. Bioenergy can provide an attractive option for countries that are producing the feedstocks of bioenergy, as any expansion of forestry would result in an overall reduction or net reductions of emissions accounted within their agriculture and forestry inventories. For the countries where they're generating bioenergies also could be attractive, because where they have bioenergy, they could be replacing fossil fuels. So where bioenergy replaces more GHG intensive energy options, they will result in overall reduction of the carbon intensity of their energy inventory. But from a climate change perspective, the location of where these emissions take place and how they are counted is pretty much irrelevant. The important calculation is calculating what the overall impact is. So the UNFCCC's CCC's accounting framework does provide a method of accounting all these emissions where they take place, but it's really important that from a climate change perspective, the important thing is that there is a balance and they are producing an overall reduction in emissions compared to fossil fuels. And a lot of stuff we do at Supergen, we do complementary analysis such as LCA, and can provide a great method of verifying where these emissions are taking place and whether in fact reductions in GHGs can be achieved through bioenergy. I think that's my final slide. If anyone's got any questions they'd like me to answer to clarify, I'm happy to do so. Okay,
thank you, Andrew. Thank you very much. We do have one question for an extremely brief response, please, and we can always come back to it if you want to go into any greater detail. But the question is, why is the release of biogenic CO2 emissions through combustion not included in the energy sector? And the person who's asking the question says they understand that it's allocated to the agricultural, forestry and other land use sector, meaning that any biogenic carbon would never leave that sector and would never be accounted for in the energy sector, even if it clearly switches to this sector for example, use as fuel in a car. So do you have a very brief response to that, Andrew?
A very brief response. Okay, the framework does provide a mechanism to account all emissions within an overall bioenergy pathway, and it is true that when you are producing a resource specifically for an energy end use, those emissions or that flux of carbon is accounted in the agricultural and forestry sector inventory, not the energy one. But as a nod to it, it is included in the energy one, but as a memo item, so you can see it's there. The fundamental answer is that the framework does provide a method of counting all emissions, so it's not as if they're being forgotten. And from a climate change perspective, it's just the important thing is accounting them, not leaving them off, and they are not left off.
Excellent. Thank you very much, Andrew, for your excellent presentation. Next we have Dr. Mike Goldsworthy, who is a sustainability manager from Drax, and he's responsibility for overseeing the carbon reporting. And today he's going to talk with us about temporal considerations for forest bioenergy. So Mike, when you're ready, please.
Thanks very much, Marcel. So for those that don't know Drax, we're a bioenergy generator based in Yorkshire, use around 7 million tonnes of certified sustainable wood pellets sourced mainly from North America and Europe to produce around 14 terawatt-hours of electricity every year. So yeah, today I'm going to speak a little bit about some of the temporal considerations for LCAs of forest bioenergy systems. So probably leads quite nicely from Andrew's presentation. Next, please, Katrina. So yeah, LCA, it's a well-established technique for evaluating the carbon flows of products and systems. But for bioenergy, often this is performed under a set of relatively restricted parameters and boundaries. And what I mean by this is that we look at supply chains in isolation without understanding the impact on the surrounding environment. But it's becoming increasingly important that LCAs for bioenergy reflect the genuine impact on the climate. And this typically relies on expanding the spatial boundaries of the LCA beyond purely that supply chain of interest. And time is a hugely important connected issue in this, and it's drawn increasing attention for us for forest bioenergy over recent years due to a potential issue carbon debt, and that's a concept I'll explain a little more in a minute. So for products that exhibit a permanent linear flow of carbon from a sink to the atmosphere, such as fossil fuels, the life cycle period for estimating that impact on climate change is usually pretty logical, starting from the point in which material is extracted from the ground and finishing at the point at which carbon is emitted to the atmosphere. However, calculating the life cycle impacts of any product that plays a more active role in the carbon cycle provides us with far greater challenges, given the difficulties in determining the temporal boundaries of that analysis. And while one might think that a common sort of cradle to grave LCA approach would typically assume a start point for the analysis to be when a raw material is produced, so when carbon is sequestered into that feedstock, a case can be made for that starting point to be any time during the carbon cycle, depending on the very specific goal of that assessment. And that choice is really quite critical to evaluating the carbon flows of the system, and indeed can be the difference between illustrating whether that system is either good or bad for the climate. So in the case of bioenergy, a justification could be made for choosing any point in the carbon cycle, including the point at which carbon is sequestered from the atmosphere, any point in which carbon remains sequestered in biomass, whether that is in the forest or within a product, or the point at which carbon is emitted to the atmosphere. Next, please. So if you choose the point at which carbon is sequestered from the atmosphere, there'll be an immediate decrease in atmospheric carbon emissions, and that'll provide a temporary carbon sink or carbon credit, if you will, that will last for as long as that carbon is kept as a fixed stock. Conversely, if you choose a point at which carbon is emitted to the atmosphere, there'll be an immediate increase in carbon emissions within the atmosphere, resulting in a carbon debt, which will require that carbon to be resequestered over time for that debt to be paid off. And that length of time is commonly referred to in biomass life cycle assessments as the payback period, essentially the time taken for the carbon cycle to complete. So any debt or indeed any credit presented from the outputs of a bioenergy life cycle analysis relied entirely on those temporal boundaries. And for short cycle products such as crop biofuels, the length of any debt or any credit is always going to be relatively brief, so typically less than 1 year. So given such a time frame is insignificant in the context of global climate change, rarely have there been any concerns raised over the temporal flows of carbon for those kind of supply chains. But when we start looking at long cycle bioenergy systems such as forest bioenergy, the length of any debt or any credit could be far longer, maybe up to 100 years for long rotation forestry. And it's this risk of a carbon debt existing for these long cycle bioenergy systems, which is regularly used as a justification by critics of the industry to why forest bioenergy is bad for the climate. That's obviously something we strongly dispute, and some of the details that I'll provide in a bit. Next, please. So when we look at a lot of bioenergy LCA modeling work to date, it's often been formed under a set of fairly restrictive parameters, taking a single point of the carbon cycle to provide the temporal scope of the analysis. And these studies can often provide reliable and accurate estimates of carbon emissions and indeed of any carbon debt or credit incurred within the confinements of those analysis boundaries. However, those results of those studies are usually highly specific to the scope and the assumptions of that analysis, and not necessarily representative of the climate impacts of the feedstock modeled, or indeed bioenergy in general, due to the importance of the factors outside the scope of that modeling, whether this is knock-on impact to the surrounding sourcing area or influencing factors on supply response, such as economic or market impact. And that's especially true and indeed relevant for counterfactual modeling of forest bioenergy, where a scenario that includes demand for bioenergy is compared to a baseline without that demand. And so regularly it's assumed that that increased requirement for feedstock has no bearing on the capability of the forest to produce additional growth over time. But more often than not, that's a hugely important oversight, and something I'll explain a little more shortly. Next, please. So when we start looking at LCAs more broadly than simply individual supply chains, for instance, when we're modeling the climate impacts of bioenergy markets or investments, it's important to recognize the resource affected by demand will not simply be biomass at a single point in its life cycle, but an entire landscape. So for forestry, this resource presents itself in all stages of growth, from newly planted forests to fully mature stands, and hence comprises biomass at varying points throughout the carbon life cycle. So you can't just pick a single point as the relevant sort of time frame for that analysis. So obviously, not only is there this time consideration, the spatial boundaries of the analysis are need to be expanded to encapsulate all carbon flows affected by demands of the bioenergy market. So that this requires modeling at this forest landscape level, or maybe even a global level. And it also requires an extensive understanding of forest management and market dynamics in that region of interest, especially when you consider that only a maximum of 2 to 4% of a forest landscape is harvested during a single year. Really important that such studies don't overlook that the potential carbon impact resulting from simply harvesting the forest, say diverting from an alternative use, but actually evaluate the impact that bioenergy market has on the rest of the growing biomass resource. And that's a factor regularly overlooked in models. Next, please. So, for privately owned forests, such as in the US Southeast, there's a wide range of potential market responses that may occur across the forest landscape to increase supply, and that's often dependent on specific local economic conditions. However, there's a broad range of logical forest management responses that are likely to occur at the economic margin across the landscape to meet increased demand for wood fiber. That includes increased forest harvesting, increased forest thinning, increased residue extraction, improved silviculture, improved forest management, increased planting, establishment of new forests, and reduced urbanization and agricultural encroachment. So a huge array of factors there. Next slide, please. And these factors have this broad range of immediate, short-term, long-term, positive and negative impact on the forest carbon stocks, including carbon stock depletion from increased forest harvesting and residue extraction, but also increased carbon sequestration through those improved practices, increased carbon sequestration through growth of new forest, through forest investment, avoidance of carbon release from burning or decomposition of forest residues, and protection against fire and disease through those improved forest management practices. Next, please. So the culmination of these impacts is that an increase in demand for wood fiber is frequently paralleled by an increase in supply. So even though it seems counterintuitive that the more wood is taken from the forest, the more wood is grown in reality, and the more carbon is sequestered in that landscape year after year. But I mean, when we look at this historical data, that cannot necessarily either prove nor disprove the existence of any form of carbon debt for bioenergy. It's essential for understanding how forest management practices, and importantly, how forest carbon stocks evolve over time and respond to meet the demands of wood fiber markets, and a high correlation between removals and growth, as we see in the forests of the US South, is illustrative of a very responsive forest landscape that will rapidly adjust to meet demands of the market. In these geographies, it's vital that those economic impacts are understood and accounted for when modeling forest carbon dynamics. And without consideration of these responses, there's a huge risk that forest management practices in the region will be severely misrepresented. So, for instance, underrepresenting yield responses to increase demand, or those impacts on forest protection. Final slide, I think. Next, please. Yeah. So, just to summarize, ultimately, it's critical that any analysis attempting to estimate the climate impacts of bioenergy does not arbitrarily assume a single point of the carbon cycle to be a relevant start point of an LCA analysis. You need these studies to consider that point to be when a biomass demand is created, whether that's a bioenergy policy adopted, a bioenergy plant beginning operation, or even when a market is created or even anticipated. And that comprises the varying growth states of biomass within that sourcing region of interest. And finally, it's really important to understand how that landscape evolves over time to meet demand, rather than simply just assuming that any supply response is always going to be equivalent between a modeled scenario with increased demand for bioenergy and the baseline when you don't have that demand. Okay, thanks. Yeah, thanks very much.
Brilliant. Thank you so much, Mike. We don't have any clarification questions for you, but no doubt there will be lots of discussion and questions during the panel session, so thank you very much. So we're now going to move on to the next presentation. So if we could have the next slide, please. That is by Nicola Noponen, who is the technical advisor at the Roundtable on Sustainable Biomaterials, and she is the sector lead in chemical and polymers. And Nicola is going to talk to us today about the overview of the sustainable principles and criteria for the standards with the Roundtable. So over to you, Nicola.
Wonderful, thanks very much. Can you hear me all right?
Yes, we can.
Super. All right, thanks very much. So, so far in the presentations today, of course, we've looked at sort of great detail into some of the methodological aspects of GHG accounting. So Andrew's talked about really a sector level approach, accounting frameworks, and Mike at the forestry landscape scale. And so we are going to look really from the perspective now of the RSB, the Roundtable on Sustainable Biomaterials. And this looks at the product level and how GHG emissions fit really into a wider sustainability framework. So how are GHG emissions accounted for, but also how do they fit into the wider sustainability agenda? And just to give you a little bit of background in case you're not familiar with our organisation, the RSB sets the standard for the sustainable production of both materials and fuels, and we do this through third-party certification, a bit like you might be familiar with FSC for wood, with one of the big differences being that the RSB standard is applicable to all feedstocks and also end products. So next slide, please. Sorry, actually, I thought we were talking to that one. Let's go on to the next one. So yeah, just to give you a bit of background then on how we incorporate GHG emissions and how that fits into a wider sustainability framework. This is an overview of the 12 sustainability principles and criteria, and these form really the core of the RSB standard. And when you look through them, you may or may not realise that climate change mitigation really feeds into many of these sustainability principles, both directly and indirectly. So if we could move on to the next slide. So when we look at some of the social principles and we think about how climate change is interlinked there, if we look at Principle 6, for example, local food security, it's understood well that food insecurity can, of course, contribute both directly and indirectly to deforestation, to land use change, and this can result in the release of greenhouse gas emissions. So, of course, good land management and good supply chain management can help to mitigate against these wider risks as well. So, under the RSB standard, we have a screening and a risk assessment process where we look at whether a region where biomass is coming from is food insecure. So we go to recognised international metrics for measuring food insecurity. And where a region is known to be food insecure, we put measures in place. So operators have to put measures in place, I should say, and meet the requirements of the standard. And these these measures would address some of the impacts that operations might have on cross-cutting requirements related to food security. So, for example, just to give you sort of practical example, you might be looking at setting aside land for food growing, or increasing yields, or providing opportunities for workers to carry out household level food production. So thinking about, you know, how you can link food security requirements in the climate context is always really, really important. Next slide, please. Okay, so looking at some of the environment principles then, of course, we have Principle 7 here, which is conservation. Principle 3, the first one you see up here, is related to greenhouse gas emissions, and we'll talk about that in a little bit more detail in a minute. And, you know, one of the really key defining features actually of the RSB standard is that greenhouse gas emissions is an overarching and mandatory requirement of all operators who are certified under the system, and therefore yeah, there's always a greenhouse gas reduction that needs to be shown for products at the end of the supply chain. But looking at some of these environmental principles then, Principle 7, conservation, so we have some fairly I would say explicit requirements relating to no-go areas, no conversion areas, conservation values in the area of operation, and of course thinking about how the conversion of high carbon stock areas can lead to quite an extreme risk of greenhouse gas emission release. But then also thinking about some of the perhaps the less obvious principles and how they relate to climate. So for example, Principle 8, soil, under the RSB standard, all operators, so by operator I mean every business or entity along the supply chain that wishes to get certified in order that an end product can carry the sustainability certification label. So it could be a biomass producer, it could be an industrial operator. Obviously for industrial operators, soil requirements don't apply because they have to be applied at the biomass level. So if we think about a biomass operator, they would have to undergo a screening process which then identifies whether a soil impact assessment and management plan are needed. And this is really important actually when we think about the bioenergy, biofuel domain, which, you know, it's received criticism about the redirection of agriculture and forestry harvest residues to fuel production, because of course this risks coming at the expense of soil quality, and we know that that can impact future land productivity as well as the carbon storage capacity of soils. So it's really important for some of these high risk feedstocks, such as those based on agriculture and forestry inputs, to actually have a rigorous sustainability framework embedded into their production that addresses all of these risks, so that the entire spectrum of unintended consequences can really be addressed, because obviously these, you know, as we're talking about now, they're very much interactive. Okay, next slide, please. And of course, these are the 3 economic management and risk management principles, so I won't go into detail on them, but next slide, please. Yeah, so obviously we know that for energy, feedstocks can come from a variety of sources. So agricultural residues, forestry residues, also primary agricultural products, and equally these supply chains can feed into a big range of end products, from fuels also to materials, you know, bioplastics, for example, and the RSB standard certifies all of these. And really, you know, when we think about the broad range of both feedstocks and end products, it shows the importance of having a consistent framework for measuring and managing greenhouse gas emissions and their wider sustainability impacts, so that they can be applied in a variety of contexts. Next slide, please. And just to note that the RSB certification does cover the entire supply chain. So in terms of GHG emissions measurement, every supplier, every step along the supply chain must calculate their respective GHG emissions. I'll go into the methods for that in a minute. And those emissions, the emissions for their product supply chain step, will always be included in what we call the proof of sustainability. So if you imagine a shipment of material that goes from a supplier to its customer, the GHG value will always be communicated on the paperwork of that shipment and transferred to the next operator in the supply chain. and that will be added to their supply chain emissions and transferred further down the supply chain, so that at the very end you have a GHG value and an impact and an emission reduction compared with the fossil baseline for the end product. Okay, next slide please. So under Principle 3, so I've talked about the 12 sustainability principles and criteria, and I noted that Principle 3 is specific to greenhouse gas emissions. So it's one of our core requirements, and the RSB standard does have specific requirements for how GHG emissions for a product should be measured, and also the minimum emission reduction which needs to be achieved in order to achieve certification. I'm not going to go into the sort of in-depth of calculations. We do have a GHG calculation methodology, but we also accept calculations using a specified range of other methodologies and tools, which I've popped up here. And also we can accept other methodologies when they've been approved by the RSB Board of Directors. But just to note that emissions are calculated always well to wheel, and we do include GHG emissions from land use change, of course. Next slide, please. And this is just an example of the type of method, the type of software that can be used for calculating GHG emissions. So, you know, there are obviously a huge number of tools out there. Operators often develop their own accounting systems in Excel, or they may have life cycle assessment software. But in order to help users who are perhaps less familiar with this process, because, you know, you imagine we work with operators who may be you know, a biomass producer, they may be a converter. There's a huge range of types of operators out there, small to large scale. And so we've developed a GHG emissions calculator which follows the RSB GHG emissions calculation methodology. And this is just a screenshot really of how that Excel tool looks. Okay, next slide please. Yeah, so under the RSB standard, there are some specific requirements related to forestry harvesting and processing residues, with obviously forest feedstocks being considered to be high risk. And this includes their method of GHG emissions calculation. And the detail really going into the specifics are available in the RSB standard. Okay, and next slide, please. And finally, just to say on our GHG emissions calculation requirements, of course, for fuels, also for materials, but as we're talking about bioenergy today, there is a mandatory emission reduction for fuels compared with the fossil baseline. So we require that all biofuels have an average of 50% lower GHG emissions compared with the fossil fuel baseline, and that's 60% actually for new installations. So that's installations, I think, since the October 2015 is the cutoff date. Okay, next slide. So we will just look into a couple of the specifics of GHG emissions and how these are addressed in the RSB standard, in addition to the Principle 3 requirement as well. So I noted that forestry residues can be considered by some as being high risk, and, you know, Mike touched upon that point in his presentation as well. But that by no means stops forestry residues from being a good source of energy. It's just a case of ensuring against the risks that can accompany them as a feedstock. And so we have, as I noted before, we have various ways of addressing them. Greenhouse gas emissions are measured through Principle 3, but we also address biodiversity issues and ecosystem management services through our principles on soil, on water, air emissions, and so forth. And we do require that all forestry residues come from sustainably managed forests. So in other words, operators who wish to get certified to RSB, who are using forest residues, forest industry residues, forest harvest residues, need to be either RSB certified or FSC certified, or following another certification scheme if it's been benchmarked and approved by the RSB. Okay, next standard. Next slide. Sorry, these are, in fact, I won't go into detail on these. These are some of the specifics on the forestry, but I think we're running a little bit low on time. So let's skip to the next one. Okay, and finally, I'll wrap up just by talking about a couple of the perhaps less obvious impacts that can occur as a result of putting bio-based feedstocks into fuel supply chains. So when we think about some of the more obvious risks, impacts to soil, for example, impacts on direct GHG emissions, these can be a little bit more clear, a little bit more easy to measure, a little bit more easy to manage. But it's also important that when we think about our sustainability framework, we think about some of the unintended negative consequences that can occur. And we categorize them into really two specific categories. One is indirect land use change, and the other is displacement effects. So if we go to the next slide. Okay, yeah, so indirect land use change, and this is, I guess probably many of you will be familiar with this term ILUC or low ILUC. So ILUC, indirect land use change, is where land that's previously used for food or feed or fibre, it's now diverted to a biofuel production. And what that means is that the previous non-fuel demand still needs to be met. And this can result in the conversion of non-agricultural land into agricultural production. So of course, this poses a real risk of deforestation and other natural habitat conversion, particularly when it involves the conversion of land with high carbon stock. It can lead to real significant greenhouse gas emissions. And I say can because it doesn't have to result in land use change. You know, there are ways to put land into biofuel production without causing indirect land use change. But to address this and to really be sure that this isn't a negative and unintended negative consequence of a biomass supply chain, the RSB has developed a set of criteria, compliance indicators, and this is for operators who need or want to demonstrate that their operations have a low ILUC risk. So we offer that as an add-on certification. If we pop to the next slide. Yeah, so the low ILUC risk certification is an add-on that it's not standalone, but it can be added to your regular RSB certification process to really mitigate against that extra risk, which of course can give access to markets which are very wary or have regulations around managing indirect land use change. Okay, and finally, last slide I think we're on. Okay, so the second indirect risk then that I noted is displacement emissions. And these are indirect emissions, again, from producing a replacement feedstock when an economically valuable feedstock is removed from the market. So, for example, just taking the case of used cooking oil. So this is quite a common feedstock to use to produce biodiesel, just as an example. But if that used cooking oil had previously been used as animal feed and it's now substituted by another vegetable oil, which could be palm oil, could be any other oil, obviously you're going to create a displacement effect there because you're stimulating the production of an alternative feedstock. And under the RSB system, again, we have a voluntary add-on standard to estimate displacement emissions and to adequately address this risk. And it's a really important one to consider, actually, because displacement emissions are common to many, many feedstocks. And without the estimation of displacement emissions, of course, the GHG emissions associated with an alternative fuel, a biofuel, can actually be far higher than they're reported. Okay, and that is it from me. Thank you very much.
That was great. Thank you so much, Nicola. We do have a quick question for you, and that is it possible to access the greenhouse gas calculator that you showed on your Excel? You had a screenshot of the Excel.
Yes, yeah, absolutely. Yeah, so our greenhouse gas calculator tool, it is publicly available for RSB members and certified operators. It's freely available, and for all other users, there's a one-off fee of, I think it's $200 US, it might be 200 euros, but you can access it through the RSB website. I'd be happy to share a link by email afterwards if you wanted to do that. But yes, it is available. Yeah. That's through the website.
That's excellent. Thank you very much. I'll just see what other questions there are. Sorry, apologies. I did miss a question at the end of the of Mike's presentation, so apologies. So I'm just seeing what else there is. Yes, so does, another question for you, Nicola, does the RSB plan to include greenhouse gas emission reductions triggered by indirect market effects as discussed in the presentation for Drax? For example, increased harvest of forest residues can trigger better forest management and increased carbon uptake. And also, how does the RSB determine the correct counterfactual for no bioenergy use, and why is the time frame maximum 20 years when forestry rotation length can be anywhere between 2 and 10 decades? So that's quite a long question, quite complicated, could take quite a long time, so maybe we could just restrict the answer to
yeah, I think
maybe just the first part to begin with, and we can maybe pick up the rest later.
Sure, yeah, I mean, when we think about for example, improved forest management, at the moment, I'd have to double check with our standards management whether there is a possibility to include this improvement that's triggered through improved forest management. We do have that provision from agricultural improvements, so we can make essentially generate a credit in the GHG calculation for improved agricultural management. And I'm not 100% sure whether the same provision would apply for forestry. However, what I would say is that for residues-based supply chains, they are assigned a GHG emissions value of 0. So where a feedstock is a waste or residue, that's the emissions value for it. Where it's a primary biomass product, like for example an agricultural product, then you calculate the GHG emissions for obviously the entire farming operation, and emissions are allocated according to either the economic value of the product or the energy content, so the lower heating value, depending on which market you're selling into, because within the EU regulated market they have specific requirements under the EU RED. But yeah, I can follow that up on. I think that's an interesting question.
That's wonderful, thank you very much. And I did miss a specific question to Drax, to Mike, about reflecting on increased demand for biomass, but he will perhaps either will touch on that in the panel or he will respond to that directly. Thank you very much, all of our speakers today, to Sam, Andrew, Mike and Nicola. You all gave fantastic presentations and kept predominantly to time, so well done. It's very difficult to do this over a webinar situation as well. So I am now going to hand over to Miriam, who's going to chair the panel discussion. So our speakers' jobs are not yet done, and they are now all open to panel questions from you all. So thank you very much. Miriam.
Thank you, Marcel. Hello, it's Miriam Roda from Aston University. I'm the topic lead of the Supergen topic systems. And I will share you through the panel discussion, which is a new format for me as well, because normally I would now say in a real world, can everybody just join us up front? And now I kind of like have to make sure everybody is unmuted when they're supposed to speak. We had asked participants to send questions in advance, because that makes it in that context a bit easier to manage questions. So we will have a few prepared questions which came already from participants. I've seen there coming questions in, and while everybody else was talking, I actually tried to respond to some of these questions, organize them. And I think some of them will all already be addressed in the prepared questions we had from participants. So Katrina, can you please go to the next slide? So we kind of like categorize the questions a bit by different topics. And we will start with the first question, which is, in case of bioenergy, carbon is sequestered and then released and then sequestered again with the regrowth of biomass. What does the delay between these two sequestration mean for the climate? And if I could ask Sam maybe to start off with a response to that one.
Sure, thank you. So, I mean, obviously the overall effect of so sequestering, releasing and sequestering, so basically delay, is to reduce an effect. In terms of quantifying that, I mean, we can give numbers for specific examples, or you could have a look at the equations yourself. Obviously, the broader question of as to whether that's a sensible way to account for it or not is a broader question. So similar to sort of some of the stuff which Mike was saying about actually how do we think about our forest system.
Okay, thank you. Mike, do you want to add to that one?
Yeah, I'll just very briefly. So yeah, it's an important point, and people like to look at it in that linear basis of which should come first. And actually, the important thing we need to look at is what's that net impact on the climate. So if we look at that cumulative resource at the landscape level, what's actually happening? Are we harvesting more than can be grown, or are we actually increasing that carbon stock year on year? So looking at that is, I think, more important question, and rather than trying to answer those questions in isolation, saying, well, how long does it take to re-sequester that carbon?
Okay, thank you. So I would suggest we move on to the next questions, because we have quite a few questions we want to get through. So the next one is, what is the nature and magnitude of the uncertainties persisted in the current calculation methods of greenhouse gas emissions, and how to address them? Andrew, do you want to have a go on that question, please?
Okay, the uncertainties can be big and they can be varied. I don't know, whether anyone who works with bioenergy very quickly realizes that nothing is black and white. There's anything modeling organic materials, there's all sorts of things that can happen. But when we do, I think one of the greatest uncertainties occurs because when we do LCA analysis at Supergen, or in this field of work, we do analysis on very specific supply chains with very specific boundaries, and the results we generate are very good, but they are very specific to those supply chains and boundaries. And I think uncertainties arise when people take outputs from LCA analysis and generalize them and say bioenergy is X, when in reality, if you read between the small print, our results are accurate to what we've actually analysed. And I think there is a lot of generalisation when it comes to bioenergy. People take one bad LCA result and say this is how bioenergy is bad, look at this. So then I think there's a great uncertainty with bad use of what we do rather than how we do it.
Okay, thank you, Andrew. Does anyone else from the panel want to address that? Yeah, I see Mike has a response.
Yeah, again, I'll try and be brief, but I think it very much depends if we're looking backwards or if we're looking forward. So anything that's backwards looking is measurable to an extent, and so you can have some degree of certainty over that. But a lot of LCA modelling is actually looking at future projections, and as soon as we start looking at any degree of future projections, comparing one scenario to another scenario, that is going to have a huge range of uncertainty, because you just can't predict how the world is going to evolve and how all these interactions are going to work. So you can address those uncertainties by understanding how, say for us, forests evolve over time, how land evolves over time in response to demand, but you can never completely remove that uncertainty.
Maybe Sam, if I pass that question to you as well, because in terms of if you bring in the temporality of emissions as well, I guess that will have an impact on uncertainties as well and change the picture a bit.
Yeah, sure. I mean, I guess it affects. I mean, at the end of the day, I suppose when we're doing this, we're thinking, what are the questions? What are the decisions that whatever calculations are trying to support? So I guess there's a source of uncertainty there. Is it actually really addressing the question that we are meaning to ask? But more broadly, I guess that's the other aspect of that, is that actually there may be some broad uncertainties due to there's a whole range of different places where you can get those. But I would think the more important aspect is whether or not it leads to the correct decisions, or decisions which can be which are beneficial and then can be updated at an appropriate timescale.
And maybe Nicola, if you, from the RSB perspective, how how much do uncertainties then actually play a role in your assessment tools and assessment frameworks? Because that might do quite some kind of like difference to different supply chains in terms of processes and how things are used or accounted for.
Yeah, I mean, I think so. We have our GHG emissions calculation methodology, and that's very much a sort of set in stone framework. But we do, we allow operators to calculate GHG emissions using other methodologies, and also where there are cases for example, calculating different scenarios, say including displacement emissions, or thinking about a situation that's very local to an operator. We of course give flexibility to take that into account, and we also, I should say that the GHG value of a product, it's calculated initially when an operator becomes certified, but certification takes place on an annual basis. So you have a main audit every 2, 3 or 5 years, depending on the level of risk of the operator. But operators also have an annual surveillance audit, and at each of these times they have the opportunity to update their GHG value of their product. And in fact, they also have the option to update that value in real time, as long as there's a good system embedded within their internal procedures for calculating that real-time value, and then they are able to report that. Yeah, so we do have some flexibility there.
Okay, thank you. So I would suggest we go to the next question, which is, how do you account for the changing substitution effect of fossil fuels, giving decarbonisation of the grid over time? And how do we compare the time-accounted global warming potential value of this bioenergy system with those of fossil fuels-based reference system? So I guess that is pretty much around kind of like the changes of also emission savings, because these will change if the benchmark will change. So Mike, do you want to have a go on that question?
Yeah. Probably the first part of that question would I'll probably touch on most, which is it's a very good question, and it's something that's sort of growing importance as the grid progressively decarbonizes. So a lot of people think of 1 unit of electricity to be the same regardless of how it's produced, but in actual fact, the utility of electricity generation can be completely different depending on how it's generated. So the likes of bioenergy is generally functions as either a base load or a flexible generation technology that actually complements intermittent generation. So when we look at displacement impacts, it's not actually in a future grid scenario, it's not going to be displacing these intermittent or rather variable generation technologies. It's actually going to complement them. And also to that, it's not purely generation it also provides system services, system stability, so inertia, frequency response, these things that as a biologist I don't fully understand, but it's just important to understand that what those technologies are that are going to be displaced, and predominantly they are going to be fossil-based generation and mainly gas. So that's how we need to monitor these kind of substitution effects over time. It's based on what are those genuine generation technologies that are going to be displaced.
Okay, thanks Mike for that. I wonder, Nicola, if that is also an issue which your customers or the companies who get your certification come up with when they consider turning more into kind of like a bio-based economy, and how relevant this is if kind of like the way we do things actually changes as well and becomes more sustainable. Okay, I can't hear Nicola. Okay, I hope it's not me. I hope it's not me dropping out. Okay, in that case, I would suggest we move to the next slide, Katrina, and go to the next question. So I just want to check, Nicola, can you hear us, or can you try to respond? Because I wanted to give that question first to you, the next one coming up. Okay, there seems to be an issue So I skipped the first question on the slide and go to the next one for now, once we have Nicola back. So the stored carbon in long-lived products could influence the carbon storage capacity in forest ecosystems and the forest product basket. So how do you account for the carbon sequestration and carbon impacts or benefits of forests supplying biomass energy as well as other forest products? Andrew, can I pass that question to you first?
Okay. Yeah, so basically, I think anything where we expand forests, we grow more forests, uptake more carbon, produce more forestry products, whether that's long-lived products or stuff we produce directly for energy, that's all good. And I think any given forest pretty much doesn't produce one thing or another, it'll produce a mix of products. So how do you account for that carbon sequestration? Well, there's different methodologies for different products. For example, for long-lived products, it's accounted that carbon is stored for a long time, and then there's a decay factor depending on what that product is. So it'll assume how long that product's lifetime is, and then before that carbon goes back to the atmosphere, it's released. And again, as I think I mentioned in my presentation, for products for energy, that decay factor is much shorter, as in it assumes that straight away those emissions are released. But how do we count it? I think anything where we're growing our forests and producing products is good from a GHG perspective, because it is producing an additional store for that carbon. I don't think I've got anything else to add.
Okay, thank you. I think we have Nicola back. Nicola, do you want to?
Yes, sorry about that.
Oh, excellent. No, that's no problem. That's the beauty of technology, I guess. We can't always control it. So if I come back to the first question on the slide, where I think it would kind of like fit quite well with your area. So can you explain how you deal with allocations in terms of burdens or credits for co-products within the system boundaries of bioenergy product systems? Well, I think it's quite interesting questions, considering that RSB is looking beyond just bioenergy, but actually looking into different products and services as well.
Yes, absolutely. So under our GHG emissions methodology, we actually, I should say first of all, RSB certifies products and fuels under a standard called RSB Global, which is where these materials and fuels are traded globally. And we also have a standard called the RSB EU Red, and this is specifically for fuels which are traded within the EU regulated market. And actually the method for allocation depends on which of those markets you're selling into. So for a global fuels, emissions are allocated to co-products on an economic basis. And under the EU Red, and this is something that's prescribed by the Commission, the European Commission, co-products have to be allocated GHG emissions based on their energy content, so using a lower heating value, and no emissions are assigned to wastes and residues or byproducts. It's only co-products that have emissions assigned to them. So I hope that answers the question. Okay,
thank you. Mike, do you want to comment on that as well?
Well, the top one or any of the other ones, is it?
Oh yeah, well, any of the other ones as well, I would say.
Yeah, I think I'd probably rather touch on probably the second or third one are a little bit more relevant, and maybe try and respond to both the second and third one, because it's a difficult question as to how you account for carbon sequestration of forest supply and bioenergy as well as other products, and it very much depends on what the purpose of the analysis is, how you're trying to account for it, whether you're looking at a supply chain assessment, whether you're looking at organizational counting of CO2 emissions, national accounting frameworks. So there's a wide variety of things, but ultimately, I mean, the important point around this is it does need to be captured and accurately represented. And I think there's this general perception that increasing demand for bioenergy has indirect impacts, and those indirect impacts are either neutral or negative. And I always feel that's a huge misconception, because there's always a huge potential for wider indirect benefits, especially when it comes to forestry, with our need to protect and maintain forestry. So I think the more general answer to that would be, well, it totally depends on what you're trying to account for, but these impacts need to be accurately calculated, or necessarily, or at least accurately represented, and must be a representation of real world data as to how forest and land more general respond to increased demand.
Okay, thank you, Mike. So, and I think that's also quite an interesting question for Sam and Andrew in terms of the kind of like increasing demand for biomass and how that can affect the wider forest system, but also in terms of when we go to the third question about actually locking up some of the carbon and products first, and then using the recycled wood, or kind of like the wood at the end of the life, for energetic uses. So that would have obviously also an impact on the carbon balance and the carbon stocks. So maybe Sam, do you want to say something on that?
Sure. So it's an excellent point. Yes, basically is the answer. There is a benefit if you can lock up carbon. I guess in terms of how you quantify that, it does depend upon the boundaries and what you have influence over. In terms of actually finding the best way ahead with that. So you can use either sort of, say, the kind of tools we've been suggesting. I think Francesco Cherubini's done quite a lot of work in terms of sort of GWP biological and stuff. So actually putting just sort of pre-calculated factors on some of that, which could be useful. But again, it depends upon the boundaries which are being considered within the LCA.
Okay, thank you, Sam. And Andrew, you have worked a lot also on waste and using waste for bioenergy, which obviously has a totally different dynamic than around the climate change impact. Do you want to say maybe something on that as well?
Yes, I have done lots of LCA on wastes, and wastes are quite interesting because, give or take, wastes are pretty much going to end up degrading and releasing carbon as they degrade, and bioenergy can provide a method of not only preventing that release of emissions as they degrade, but sometimes mitigating large counterfactual emissions. Did a lot of work on wet organic materials such as slurries and manures. We talked a lot about forestry today, but there are obviously lots of types of biomass. So there are bad practices that take place in how these materials are currently managed and got rid of. And through bioenergy, for example, anaerobic digestion, for example, is a pathway. In our LCA analysis, we found that by mitigating counterfactual emissions where that material is stored or spread in a really bad way, bioenergy can result in overall net negative emissions if you were to assume that those counterfactual emissions have been mitigated. So wastes are a very interesting dynamic for bioenergy because you have to assume what that waste would otherwise be used for and how it would be dealt with. So yeah, waste is, from my perspective, is a win-win in terms of energy, as long as we're doing it in a clever way.
Okay, thank you, Andrew. So being very conscious of time, that we're actually running over 3 minutes now. Katrina, where we leave that one and go to the final slide, please. I would suggest we finish here with our questions. We had another question on BACs, but that could actually be another webinar we should think about in Supergen. So Katrina, if you could go to the last slide, please. Excellent, thank you very much. So I would say we end here our panel discussion and our webinar. I want to say thank you to the presenters for their brilliant presentations and taking time over lunch in the UK to be here with us. Obviously, also thank you to Marcel leading us through the seminar. A big thank you to Katrina Heaton, who sits in the background and clicking the slides and has actually organized the webinar. So we wouldn't have that webinar without Katrina's brilliant skills on getting everything done and getting everybody online. And also, obviously, I want to thank our audience, our participants. Thank you so much for spending time with us. I'm very much aware that a lot of people from all kinds of geographical regions have joined us. Some probably just got out of bed, some just about to go to bed. So thank you very much. I think that is the wonderful thing about having a webinar, that many more people can join than just coming to kind of like a physical workshop. So thank you very much. thank you to everybody who sent questions. We tried to respond to some of the questions during the webinar. We have published some of the questions. Thank you to the people who have sent questions beforehand, which is actually quite handy. That would be kind of like my giveaway message of the webinar. If you have to organize a webinar, ask people to send questions beforehand, because then you can organize the discussion much better. And you can make sure if people send similar questions that you cluster them. So thanks everybody. If you want to know more about the Supergen Bioenergy Hub, you see the slides with all the detailed information to get in touch with us via Twitter, via LinkedIn, or our website. The policy briefs which were presented by Sam and Andrew are already online. So there are full policy briefing papers on that on the website. And we will send out our this presentation and the recording after the webinar. And if you have any further questions, there's also our email address. So get in touch with us. So thank you very much, everybody.